All right, so if you go back to where we were at the end of Wednesday's class, Wednesday we introduced our first two gas laws. We introduced Boyle's law, which gave us a relationship between volume and pressure. And we introduced Charles' law, which gave us a relationship between volume and temperature. Now, what we're going to do today is largely we're going to focus on how do we start putting these together into something a little bit more, a little bit bigger. So before we get into that, let's take a moment and do an example problem using Charles' law, just so that we have a little bit more context and that we can understand it a little bit better. Did we do this one already? Okay. All right, so let's move on then. Up until this point, we have focused on just isolating two of those measurables against each other and holding everything else constant. Well, what if we don't have a situation where that's possible? What if you're looking at a situation where we have volume and temperature and pressure all capable of changing all at the same time? And this is a real situation, because most of the time, let's take car tires, for example. If I have a severely deflated car tire, or even one that's just slightly deflated, and I start warming up the gas inside, either through using warm gas, or I start driving and through the motion of the wheels, the tire warms up, and so the temperature warms up. I'm going to notice that the tire itself is probably going to expand some during that driving and warming period. If we are in that situation where multiple things are changing at the same time, what we're going to do is we're going to use what is called the combined gas law. Now, the reason it's called the combined gas law is because it is the result of the combination of Boyle's law and Charles' law together. So just to remind ourselves here, we can see in this pink equation there's our Boyle's law. And if we look at this blue equation, there we have Charles' law. So the combined gas law is aptly named because it is the combination of those two gas laws that we previously described. And what this allows us to do is it allows us to calculate what's going to happen to my gas if multiple things are changing at the same time. Now, notice here, this part's also important. The number of moles of gas, or the amount of gas, is still constant. So I'm still talking about a trapped gas of some kind with the combined gas law. But what I'm seeing here is that this combination of Boyle and Charles allows us to look at that trapped gas and modify how it is being manipulated. So I could take this balloon and drop it into an ice bath. And modify its pressure and be able to monitor everything about it. So let's take a look at an example problem involving this. Let's say that we have a sample of gas that is initially at 158 milliliters, 735 millimeters of mercury for its pressure, 34 degrees Celsius for its temperature. If we compress the gas while warming it, what will the final pressure be? So the combined gas law, P1 V1 over T1 equals P2 V2 over T2. This is what we're going to use. What we have to do is identify what are our initial conditions, we'll call those 1, and what are our final conditions, we'll call those 2. So our initial condition, V1, is 158 milliliters. So I'm going to put that in right there. Important thing for us to identify. Like with so many of our other equations from previous chapters, when it comes to volume, so long as my volume units are the same, I don't have to change them. So the fact that this is in milliliters is okay, so long as my other volume unit is also in milliliters, which it is. If they weren't the same, I would have to convert one to the other so that we can get them to properly match up in the equation. Same thing with the pressure units. Pressure units, so long as they are the same, it doesn't matter what they are. For temperature, it has to be Kelvin. Can't be anything else because temperature has to directly relate to energy, and the Kelvin scale is the only one that does that. So I've got my initial volume, 735 millimeters of mercury, that's my initial pressure. My initial temperature is 34 Celsius. I've got to turn that into Kelvin. 273 plus 34. Gives me 307 Kelvin. On the other side, I've got 108 milliliters. That's my second volume. The question is asking me for the final pressure, so I know I'm not going to be able to get that out of the problem. That's what I'm solving for. (85 degrees Celsius), that's my final temperature. So I gotta turn it into Kelvin first. So 273 plus 85. (358 Kelvin). Okay, before we do any algebra here, thinking in terms of our gas laws, we can probably make a prediction about what's going to happen here in terms of the pressure. we see that our volume has gone down. Decreasing the volume according to Boyle's law would increase the pressure. So we are thinking, at least on those terms, that the pressure should go up. Now, we didn't talk about this relationship in particular, the relationship between temperature and pressure. This is something called Gay-Lussac's or Hamilton's law. But from the equation itself, we can see that the equation is similar to Charles' law. Pressure over temperature, just like volume over temperature. That would indicate a direct relationship. So the fact that our temperature has gone up would tell us that the pressure should go up as well. And so in both cases, the gas laws individually are telling us that the pressure should go up. So I should expect an increase from the 735 that I calculate P2. If I don't get an increase, that's a sign that I might have done something wrong. To get pressure by itself, I need to multiply each side by 358 Kelvin and divide by 108 milliliters. When I do that, everything cancels on the right side except for P2. The Kelvin cancel and the milliliters cancel on the left side, leaving just millimeters of mercury as my unit. Now I just need to do the math. 358 multiplied by 158 multiplied by 735 divided by 108 divided by 307, the three significant figures, we get 1,250 millimeters of mercury. Is 1,250 greater than the 735 that we started with? Absolutely. So we know from a logical standpoint that we're at least on somewhat good footing in terms of what our answer is. Logically speaking, we knew it went up. It did go up. It went up relatively significantly. So that should tell us, okay, I can feel good at least from a logical standpoint about this answer. I put it into mastering and hopefully it's correct. If it's not, then I know that logically I'm okay. Maybe I need to go back and check my algebra. Make sure I copied all the numbers down correctly. Questions on this example problem before we move on to something else? Okay, so before we move on to another more complicated gas law, let's look at a simpler gas law that's actually going to feed into that. I want you to think about the relationship between the amount of gas and the volume of the gas sample. If I increase the amount of gas in a balloon, what happens to the balloon? I hope it's not this one. But in general, yeah, we're all on the right track. And again, even if you knew nothing about the gas laws, you understand this concept. You blow up a balloon, the balloon gets bigger. So what is this relationship actually called? We refer to this relationship as Avogadro's law. Now, Avogadro's law is related to that same Avogadro that you have been secretly cursing in your sleep since the advent of the mold concept that many weeks ago. The one that gave us Avogadro's number, 6.02 times 10 to the 23rd. It's that same guy. But the relationship here is important. The volume of a gas is directly related to the amount of gas, assuming constant temperature and pressure. And since most of the time we can assume constant temperature and pressure if we're just looking at a gas at room temperature and atmospheric conditions, this relationship holds pretty close to the vest. It's a direct relationship, it's a direct proportionality. And like we saw with the other direct proportionalities, with Charles' law and with Gay-Lussac's law, direct proportionalities show up as ratios, fractions. The volume divided by the number of moles for one gas at one set of conditions is equal to the volume and moles for the same gas at different conditions. So let's take a look at another example problem. Let's say that I have 0.22 moles of helium, and that 0.22 moles of helium takes up 4.8 liters of space. If I want my balloon to be 6.4 liters, how much more helium do I need to add? So using Avogadro's law, V1 over N1 equals V2 over N2. I know that I'm starting with 4.8 liters, and that contains 0.22 moles. And I want it to go up to 6.4 liters. Question is, how many moles would that be? Now, in this particular case, we could solve it algebraically. If we were going to solve it algebraically, the thing to do would be to flip it, then do your algebra. If we flip it, then do our algebra. The reason that works is that it's going to put our unknown in the numerator, which will make it easier to get rid of the other factor. So 0.22 times 6.4 divided by 4.8, two significant figures, would be 0.29 moles. So in total, we need 0.29 moles to get to that volume. To answer the question, how many additional moles? We started with 0.22 moles, so we need to add 0.07 moles more to get us to that spot. Now, the other way that you could have solved this is recognizing that this is a proportionality, you could have cross multiplied and solved algebraically that way. In this case, I actually just like flipping the fraction a little bit easier because if you're flipping both sides, it does nothing to the overall product. But it makes the math a whole lot easier because if you divided each side by 6.4, you would have ended up with 1 over x instead of x, and you would have ended up with an answer that didn't make as much sense. Whatever the reciprocal of 0.29 is, 3.41. And that wouldn't have made any sense. You would have typed that into mastering or whatever, and it would have been way off. So the thing is, algebraically speaking, if you have a variable in the denominator, if it's possible, flip both sides of the equation to get that variable in the numerator, and then it's a lot easier to solve algebraically. All right, questions with this example? Okay. So this is where we start to put it all together. This is another version of a combined gas law. We are combining Boyle's law, Charles' law, and Avogadro's law together. Now, this is not called the combined gas law. It's something called the ideal gas law. And what becomes important for us out of the ideal gas law is, in the ideal gas law, rarely are we actually tracking changes. Because it doesn't usually make sense to track changes when I'm trying to look at all 4 of those measurable parameters at the same time. Instead, what the ideal gas law usually gets used for is, if I know 3 of the parameters of a gas, I can use the ideal gas law to solve for the 4th parameter. So if I know the pressure and the volume and the temperature, I can use the ideal gas law to figure out what the amount of gas is. If I know the amount of gas and the temperature and pressure, I can solve for the volume. So your book presents the ideal gas law as this: V is equal to RNT over P. But most places will in fact rewrite that relationship like this. The ideal gas law is most commonly written as PV is equal to nRT. And so again, no 1s and 2s in this particular equation because we don't need it. Rarely are we going to be using this particular gas law to understand the relationship between a gas that is changing temperatures and pressures. Instead, we're going to use it more often to help us to describe a gas more fully. Now, the value of R here, R is something called the ideal gas constant, and it is equal to 0.0821 liter atmospheres divided by mole Kelvin. Now, why that particular unit combination? Well, that unit combination allows us to use R to cancel out the units of the things that we know to get us to the things that we don't know. So if I know the pressure and the volume and the temperature, and I'm trying to solve for N, I'll be able to cancel pressure, volume, and temperature out of my gas constant there and be left with only moles. Now, in this particular application, because the units have been set so in such a way, these units have been set. So because R sets the pressure unit as atmospheres, we have to use atmospheres. Because R sets the volume unit as liters, we have to use liters. We were already going to use Kelvin temperature because we can't not use it because of the way that it's being applied. And for N is always moles anyway, so that part hasn't really changed either. So what that means is that if we have units of pressure or volume that are not liters and atmospheres, we're going to need to convert them. And probably the most common places for that would be if we were given milliliters instead of liters, we're going to have to convert the milliliters to liters by dividing by 1,000. If we're given torr or millimeters of mercury instead of atmospheres, we're going to have to do that conversion. Let's take a look at an example problem. What is the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin? Well, if I'm using the ideal gas law, PV is equal to nRT. One thing that I can do is, if I understand what variable is missing, I can manipulate this equation before I start putting numbers in to make it easy. And what I mean by that is I'm supposed to calculate the volume here, which means I need to get V by itself. Rather than do my algebra beforehand, I'm going to do my algebra right now. To get V by itself, I need to divide both sides by P. And so my equation, V, is going to be equal to nRT over P. Again, the reason I do this here is because it's a lot easier to manipulate this before I start throwing numbers and units in. Now that I know exactly what it is that I need to do and exactly the order that it needs to go in, now I can just plug in my values accordingly. So my 8.845 moles, that's my N. My R is 0.0821 liter atmospheres over moles Kelvin. My pressure is 1.37 atmospheres. That goes in the denominator. And my temperature of 315 Kelvin is the last thing I need in the numerator here. Now we can see why R is labeled the way that it is. I've got moles up top and moles on the bottom, so they cancel. I've got Kelvin on the top and Kelvin on the bottom. It cancels. I've got atmospheres up here and atmospheres down here. They cancel. The only unit that is left is the liters. And liters are a volume, which is what I'm trying to find. Now I just need to plug the numbers in. 0.845 times 0.0821 times 315 divided by 1.37 to three significant figures because all of my numbers here have three. I get 15.95, which you're gonna have to round up to 16.0 liters. Like I said, where this particular gas law is good for us is helping us to describe what we don't know about a gas. So if I know the amount of gas and the temperature and the volume, the pressure, like I did here, I can use the ideal gas law to solve for volume. If I know volume, temperature, and pressure, which are three pretty common things to measure, I can turn that around to figure out how many moles of gas there are. And that's where this particular gas law has its greatest power. Now, we'll get to some examples maybe on Monday during our cleanup time. But we'll get to some examples where that information might be the most useful to us in terms of trying to figure out the molar mass of a gas just based off of measurables or other kinds of applications like that. So here's an example of that. Here I have a pressure, a volume, and a temperature along with a mass. I can use this kind of information to do two things. First of all, I can find the number of moles. So if I'm solving for N, I need to divide both sides by R and T. So N is equal to PV over RT. And molar mass, remember, is grams divided by moles. So if I know the grams and I can solve for the moles, I can figure out the molar mass of the stuff without even knowing what it is. Just by measuring its mass and measuring its temperature, volume, and pressure, I can calculate the molar mass of the gas and actually use that to figure out what it is, or at least get us a good idea of what it might be. So my pressure was 1.06 atmospheres. My volume was 0.112 liters. R is still 0.0821 liter atmospheres over moles Kelvin. And my temperature is 298 Kelvin. Again, we can look and see that atmospheres is in the numerator here and the denominator here, so they cancel. Liters is in the numerator here and the denominator here, it cancels. And then within the denominator, Kelvin is in the top part of the fraction and the bottom of this one, so it cancels. What I'm left with is 1 over moles in the denominator. And so if I'm taking 1 over moles, that whole thing flips over, I end up with moles as my unit. So I'm going to get moles as my unit here. Calculation 1.06 times 0.112 divided by 0.0821 divided by 298. Again, to three significant figures. I'm getting 0.00485 as my moles. Find molecular weight or molar mass. I need grams over moles. My grams are 0.136 grams. My moles I just calculated 0.00485. Three significant figures, I get 28.0 grams per mole. 28.0 is pretty close to the molar mass of nitrogen. Nitrogen atoms are 14 each. Nitrogen as a gas is N2, so 2 times 14 is 28. My best guess, at least at this point, would be that this is in fact nitrogen. It could be other things. It could also be something like carbon monoxide. Carbon monoxide, carbon is 12, oxygen is 16, 12 and 16 together are 28 and 12. So this would at least narrow down the possibilities of what that gas is. All right, questions with this application? Okay, so the last part of this particular chapter is, well, what happens, how can we use the ideal gas law and plug it into the concept of stoichiometry? And the answer is, basically, I can use my pressure and volume and temperature measurements to solve for the number of moles. And the thing with stoichiometry is, once I figure out how to get to moles of a substance, the rest kind of falls into place, because I can use the balanced chemical equation to figure out the number of moles of another substance from my moles of gas, and I can kind of rock out the rest of the way from there. But I'm going to be real honest with you. Even though this particular manipulation of the ideal gas law is covered in your book, I am not entirely convinced that this is the appropriate forum for this kind of discussion. In Chem 105, yes, we do a lot of these kinds of calculations when we talk about gases. For here, I don't think necessarily that this is the best way to do the ideal gas law. Is it technically good and correct? Absolutely. Is it necessary for what I need you to understand about gases and the ideal gas law? I'm not entirely convinced. So what I want to show you, and this is probably going to be where we spill over into Monday, is I want to show you a particular situation where stoichiometry might be a more appropriate kind of context. And it's this. There is a set of conditions for temperature and pressure known as standard temperature and pressure. Now, standard temperature and pressure specifically refer to 0 degrees Celsius and normal 1 atmosphere pressure. Now, as far as we're concerned, the 1 atmosphere pressure makes a lot of sense. That's where we do most of our work. The 0 degrees Celsius, that's a little cool. I mean, we're talking about 32 Fahrenheit there. That's probably a little colder than what most of our labs are kept at. But that's been what has been determined to be standard temperature. Now, here's the thing. One of the extensions of Avogadro's law is that we can maintain something called a molar volume for a gas. And what the molar volume of a gas basically says is, because Avogadro's law is so consistent for ideal gases, The identity of the gas itself doesn't matter. If I have 1 mole of gas at these standard conditions, regardless of what the gas is, it will take up 22.4 liters of space. And what this allows us to do is, instead of using the ideal gas law, if we maintain our conditions at standard conditions for our chemical reactions, we can use this relationship as a conversion factor. Meaning, if all of our reaction is done at STP, at standard temperature and pressure, all I need to know about a gas is its volume to convert it into moles. Because the standard temperature and the pressure, they account for those other conditions. And Avogadro's law tells us at those conditions, 22.4 liters is the volume. Doesn't matter what the gas is. So on Monday, we'll cover this last little concept here. We'll do an example or two of how to apply it, just so that you can see it and see it in action, how it applies to the other stoichiometry questions that you did in the last exam. That's where we'll leave it out for today. Make sure that before you leave, you get this last question in so that you get that participation point in addition to your other participation points for today. And by all means, it's not going to be the greatest weather in terms of temperature, but it is going to be kind of nice in terms of sunshine. Have a great weekend.